We all know what DDR stands for, right? Double data rate. The thing is, that's double the rate from, 1996. There's an idea whose time has come and gone. It's like having a twice as good 8-track tape or a double-speed IBM Selectric typewriter. Now, I'm not trying to bag on SDRAM. That's about as useful as complaining that the ocean is full of salt water. But this doubling that DDR is so famous for hasn't kept up with every year 2-year doubling of Moore's Law. So, while DDR is still the dominant memory technology in, everything, there's lots of applications where DDR, even DDR4, just can't cut it. And for some of us, that's a problem. Hi, I'm Amelia Dalton, host of Chalk Talk. Of course, we've had DDR2 and DDR3 and now DDR4, and those are all just fine and dandy, but for some applications, we need more memory bandwidth. A lot more. My guest today is Darren Zacher from Xilinx, and we're going to talk about high bandwidth memory, or HBM, and how it can deliver more bandwidth than you ever imagined possible. And before we get started, don't forget to click that link. There you can find out more information about high bandwidth memory solutions from Xilinx. Hi, Darren. Thank you so much for joining me today.
Thank you, Amelia.
So, you say insatiable bandwidth. Now, what specifically are we talking about here?
Well, specifically, I'm referring to memory bandwidth. We've been tracking the trends of the various markets we serve with our all-programmable devices, and we continue to see increasing bandwidth requirements across several markets. In networking, many of us already enjoy the benefits of a 10x expansion in network throughput over the past 10 years.
Sure.
In video, we're already well on our way past the original HD spec toward 4K and 8K, and eventually even 16K video for incredibly sharp images. We're also seeing increasing use of DSP resources for compute-intensive functions like image and video processing and applications like deep learning to improve the performance of automated tasks such as recognition and diagnosis, even autonomous control. All of these advances require a tight coupling between logic and compute resources and working memory.
Sure.
And because many system designers today are still using DDR as their first choice for memory, we would expect that an increase in Ethernet, DSP, or video performance would be matched with an equivalent increase in supporting memory bandwidth. Unfortunately, that hasn't been the case.
No?
Not really. Before 2008, life was pretty good for a system designer. Ethernet line rates were just barely ramping up to 40G. The max DSP performance in FPGA was around 1.2 teraops, and video was ramping up to 7.5 megapixels at 120 frames per second. The memory bandwidth requirements of all of these applications were easily met by a bank of DDR3.
Okay.
Fast forward to today, and you see that Ethernet line rates, DSP compute power, and video pixel and frame rates have all increased by 5-fold or more.
Right.
Meanwhile, in that same time, the heralded upgrade from DDR3 to DDR4 brought with it only a 20% increase in memory bandwidth.
Ah, okay.
So as a result, despite commodity DDR being optimized for cost and capacity, there are many applications that simply cannot rely on commodity DDR to meet their bandwidth requirements today. Thus, the memory bandwidth gap.
Okay, Darren. So if there is such a gap, then what do you think has to change?
Well, the easy answer would be that memory data rates need to go up, but unfortunately, it's not that simple. Let's take a look at how you determine memory bandwidth.
Perfect.
It's essentially the data rate multiplied by the data width. So if you want more bandwidth, then you need to make one of those numbers bigger. The maximum DDR4 data rate supported by today's FPGAs is 2.666 gigatransfers per second. So for a 64-bit commercial DIMM using that data rate, you're looking at a bandwidth of about 21.3 gigabytes per second.
Okay.
If your system requires more than that, then in order to meet your requirement using DDR, you'll need to design in additional DIMMs or components to increase your data width, or DQ bits.
So something tells me throwing more memory at this problem will only help so much.
You're right. More memory can't always be the answer. Additional DIMMs or components come with their fair share of challenges, including both PCB-related challenges as well as power consumption, which we'll talk about in turn.
Cool.
On the PCB side of things, the most obvious challenge comes from form factor limitations. Using DDR components for a 40G Ethernet port was relatively simple and could be accommodated in a pretty tight form factor using 4 by 16 DDR components per port.
Okay.
As the Ethernet line rate grew to 100G, the task became more complicated, using between 12 and 16 components per port, but was still technically doable, though more expensive. Routing complexity and even signal layers would have likely increased in order to accommodate the additional DDR components on the board.
Sure.
Now, as we scale up to 400G, the number of DDR components required to meet the associated bandwidth requirements gets pretty crazy.
Yeah.
The number of DDR components required is too many to even fit on my slide.
Right.
Obviously, this is not going to work. It's not something that you would try to build. Put simply, this approach of adding components in order to increase bandwidth does not scale well.
Yeah, I can see that for sure.
But PCB challenges are just one part of the problem. We need to look at power as well. This is another area where DDR doesn't scale well.
Okay.
The DIMMs themselves each consume power, more than 4 watts each. There is a bit of power consumed in the FPGA by the interface logic, etc., but most notably, even more power is consumed by the I/O connecting to the DIMM than by the DIMM itself.
Ah, okay.
That totals about 10 watts of system power per DIMM. So if my primary requirement is bandwidth, then a multiple DIMM solution is actually a very expensive solution from a power standpoint.
Hey, I guess so.
What I'm trying to say is that for applications that have a significant bandwidth requirement, a breakthrough increase in memory bandwidth is needed.
So let me see if I got what you're saying right. DDR is bandwidth limited. And so for high bandwidth applications, there's a high price to pay in terms of PCB complexity and power consumption to using DDR.
That's right. Again, DDR is a tremendous solution if cost and capacity are your primary concerns. And because of that amazing capacity per dollar, DDR has become ubiquitous in systems across multiple industries, and we provide leading DDR support in our devices. But for those applications that require higher bandwidth, another alternative could be very helpful.
Yeah.
So, what are the alternatives? Well, one way to help alleviate bandwidth concerns is to reduce latency. So, one alternative is to go for a lower latency DRAM, such as RLDRAM. While its bandwidth is actually lower than DDR, it has inherently very fast access times, allowing you to process things faster, and thus it could be a really good choice to meet that need. RLDRAM fits very well, particularly in packet buffering.
Okay, so in some cases, reducing your latency with RLDRAM is sufficient.
Right, but for many high bandwidth needs, the solution that's been talked about most to date has been Hybrid Memory Cube, or HMC. HMC offers impressive bandwidth at 160 gigabytes per second. Many of today's FPGAs, including those from Xilinx, support interfacing with HMC. Xilinx also provides memory controller IP. But one of the biggest drawbacks of HMC is the cost in terms of transceivers. Achieving the full bandwidth spec requires using 64 of your precious high-speed transceivers for the HMC memory subsystem. Depending on your application, you might not have this many transceivers to spare.
Right. So, while the bandwidth is impressive, that's a pretty hefty price to pay for using it.
Exactly. And that brings us to high bandwidth memory, or HBM. HBM-enabled FPGAs offer nearly 3 times the bandwidth of HMC at a far superior power consumption per bit of bandwidth without any of the PCB complexity and not requiring the use of any of your precious transceivers.
Yeah, 460 gigabytes per second is a huge amount of bandwidth. So how does HBM work?
Well, in a nutshell, HBM is a true 3D stacked DRAM chip with 4 through-silicon via DRAMs stacked together on top of an ASIC.
Okay.
The second generation HBM2 JEDEC spec is supplied by multiple DRAM vendors, offering a full 128-byte data width per die stack. The HBM address space is broken into what are called pseudochannels, each being able to address a portion of the total address space. We'll talk more about the implications of that later.
Okay.
HBM is intended to be co-packaged with another silicon die, be it a processor or an FPGA, using wide, high-speed in-package interconnect. Integrating like this actually increases the thermal density of the package, but reduces the overall system power and thermal load.
Cool.
So for many system designers, it's a really attractive option. And since the high-speed interconnect that joins the memory to the co-packaged die is entirely within the package, this eliminates all the PCB complexities normally associated with DDR interfacing.
Okay, that does sound like a really attractive technology in terms of power and PCB complexity. But how does this work with an FPGA, Darren?
HBM-enabled FPGAs can be built using the same stacked silicon interconnect technology, CoWoS, that's been used successfully now for 3 generations of 3D ICs.
Okay.
It's actually the same assembly approach that Xilinx has been taking with our high-end 3D ICs since 7 series. A passive interposer with microbumps carries the high-speed interconnect routing between the FPGA and HBM die. An all-microbump connection offers 20x the bandwidth per area of a C4 bump connection required by a DDR interface, since the C4 bumps on the bottom face of the interposer are 20 times the size of the microbumps on the top face. Having no C4 bump connections or PCB trace length means a much lower capacitance, making this method ideal for building high bandwidth connections between chips, such as for 3D ICs.
Nice. So a pretty mature assembly process is available. Now, you mentioned high bandwidth connections. Is that why HBM is so good for bandwidth?
Partly, yes. The high-speed interconnect is a key factor. Another key component is the wide data width to the stack, a full 1024 bits or 128 bytes. That's 16 times the data width of a DDR DIMM interface. At a 1.8 gigatransfers per second data rate, we can revisit our bandwidth calculation to see that the memory bandwidth offered by a single stack of HBM is 230 gigabytes per second. That doubles to 460 gigabytes per second when 2 stacks are integrated.
Okay.
That means with 2 stacks of HBM, you can realize 20 times the bandwidth of a DDR4 DIMM. And with such plentiful bandwidth, an attractive power profile, and simplified PCB design, HBM lets designers focus on doing something awesome, not just on meeting spec.
That would be nice. Darren, do you have an example of where HBM would be really useful?
Sure do. Here's an example of what a 400G Ethernet smart network interface card would look like if you managed to implement it with DDR4. Even with 4 DIMMs and occupying a full-height, full-length PCI Express form factor, you still wouldn't be able to achieve the full 400G Ethernet line rate.
Yikes! And I suppose it would have a pretty hefty power drain with those 4 DIMM modules?
Absolutely. Now, substitute an HBM-enabled FPGA, and you're able to essentially integrate all that memory bandwidth into the FPGA package, leaving you with basically the FPGA and the optics on the PCB, now able to run at the full 400G line rate.
All right.
This allows you to easily meet the smaller half-height, half-length PCI Express form factor and brings down the power consumption considerably by removing those 624 IOs that connect to the DIMM interfaces. Lastly, the PCB design exercise becomes much simpler, with fewer layers and reduced manufacturing cost as a result.
Excellent.
Plus, your application would see a 5x increase in memory bandwidth over using 4 DIMMs, allowing you to achieve the full 400G line rate, so your design team could be focusing their energies on how they can take advantage of all that memory bandwidth to differentiate your product.
Yes. Now, I can definitely see the advantage here. So, we've talked quite a bit about the problem of scarce memory bandwidth across several applications, and we've looked at alternatives for how to fill that memory bandwidth gap, including the use of HBM. So, what does Xilinx bring to this party?
Well, in late 2016, Xilinx announced our Virtex UltraScale Plus HBM-enabled FPGAs, built upon our proven Virtex UltraScale Plus FPGA family. This family represents the highest computational power for the highest bandwidth applications. It features TSMC's 16nm FinFET programmable fabric, up to 21.2 teramax of DSP performance, that's 28.1 teraops per second of INT8 DSP, up to 96 33 gigabit transceivers, plus many high-performance integrated blocks, such as 100G Ethernet, 150G interlocking, RSFEC, PCI Express Gen 3x16, and Gen 4x8. Virtex UltraScale Plus FPGAs are shipping in production quantities today.
Seems like a proven foundation then.
Exactly. Our Virtex UltraScale Plus HBM devices build upon that foundation with up to 2 stacks of high bandwidth memory using our 3rd generation CoWoS silicon stacked interconnect technology, an integrated HBM controller designed to maximize effective bandwidth to the HBM. the HBM2 specification delivering the highest bandwidth available today. Standard AXI interfacing to the HBM controller for easy integration using the Vivado IP integrator, and integrated cache coherent interconnect, or CCIX ports, ideal for acceleration.
So, innovative memory technology delivered on a proven foundation using proven assembly technology. That sounds pretty nice to me.
You got it. And while we are building on a proven foundation and using proven assembly technology, we're offering our own innovation in areas that we believe will provide tremendous value to designers. The first of which is in the HBM controller design.
Okay.
Here, we're providing an integrated controller block that's proven and ready to use, so designers can start designing with HBM right away using Vivado's IP integrator. The memory controller uses hard AXI channels to interface to the programmable logic. These channels are physically extended into the fabric to ensure efficient routing to the HBM controller interface. The memory controller also incorporates flexible addressing to allow any AXI port to access the entire HBM address space, effectively overcoming the pseudo-channel separation I talked about earlier, normally inherent to HBM. Flexible addressing gives tremendous flexibility to the designer to choose AXI channel sites that minimize time enclosure effort.
Interesting. Okay. Darren, can you give me an example of this?
Sure. Let's take a look at a simple traffic manager example. Here, packets come in through the 100G port, are written to the HBM by the packet writer logic, read from the HBM by the reader logic, then exit through the interlocking port.
Okay.
Without flexible addressing, due to the pseudo-channel separation inherent to high bandwidth memory, the packet writer would need to connect to several AXI channels in order to access the full HBM address space, resulting in the logic spanning the entire width of the memory controller.
Right. Okay.
Likewise, the packet reader would need to connect to several AXI channels in order to access the full HBM address space. This would lead to a fair amount of congestion near the HBM controller, which might complicate time enclosure.
Right.
Now, with flexible addressing, the packet writer and packet reader can connect with just the nearby AXI channels to the HBM memory controller, such that the logic regions do not overlap. This reduces congestion and allows for much easier time enclosure.
That could be very helpful for designers to overcome those pseudo-channel separations we talked about earlier.
Exactly. It's a tremendous benefit to be able to access the full address space from each and every AXI channel. And because any user-accessible AXI interface can access any address in the HBM memory space, it makes them far more efficient from a utilization standpoint. Now, the second area where we are innovating is in package design.
Okay.
I mentioned earlier that HBM is intended to be co-packaged with another silicon die, and that while this co-packaging increases thermal intensity of the package, it results in overall reduced system power and thermal load.
Yeah.
Well, for our Virtex UltraScale Plus HBM devices, we are using heatsink-ready, lidless packages that significantly improve cooling to alleviate the higher thermal density. These packages are already shipping in our other Virtex UltraScale Plus FPGAs, where they have been shown to improve cooling by about 10 degrees for most use cases.
Very cool. Literally. Okay, so a designer can get the best possible package to manage their thermal load. You mentioned packages, so are there several HBM devices in the family?
That's right. 4 family members provide scalability both in terms of computational power, transmission bandwidth, and HBM bandwidth. You can see a quick overview of our family members here. Our smallest system logic cell device comes in both a single and dual HBM stack configuration.
Got it. So there's a whole family of HBM-enabled FPGAs to choose from depending on your particular needs.
That's right. And like we said earlier, at Xilinx, we've been able to focus our innovation on where it will help designers the most. Where we're not focusing innovation, these Virtex UltraScale Plus HBM devices are building upon a proven foundation of silicon process and architecture, assembly technology, and design tools.
Seems like a win-win to me.
I think so. Like we saw, while many of tomorrow's systems exceed the bandwidth offered by DDR, we are seeing that high bandwidth memory is the best alternative for boosting bandwidth on a power budget. And so we are building the Virtex UltraScale Plus HBM devices to provide the right mix of memory bandwidth and programmable compute logic. If you're interested in learning more, go ahead and click the link below or point your browser to www.xilinx.com/memory.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Darren.
Thank you, Amelia.
And before we go, don't forget to click that link
There you can find out more information about Xilinx's HBM solutions. For Chalk Talk, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to YouTube, keyword eejournal, or check out the on-demand section of eejournal.com.